start recording. Okay. All right. So I'll just recap what I said. So we normally did accelerations with where AX was 0. But now in this particular question, we're going to have AX. We're going to have AX now, right? And what's important there is that when we typically have that kind of acceleration, we typically take other factors such as air drag, surface friction, or the engine itself has particular accelerations, obviously, to accelerate the plane. So in this particular question, we will be solving a two-dimensional problem with having two accelerations. We know that in the AY, we have the gravitational, and the AX, it will obviously be the particular acceleration of the object. But let's look at the illustration. So we've got a jet plane traveling horizontally at 100 meters per second, I believe. Drops a rocket at a considerable height. Right, and say the rocket immediately fires its engines, accelerating at 20 meters per second squared. So you can see there, that's it's already telling you that. So they're saying that's in the X direction, while falling under the influence of gravity in the Y direction, right? So obviously that is directly telling you there are two accelerations, right? Then they're saying when the rocket has fallen 1 kilometers, find the velocity in the Y direction, B, the velocity in its X direction, the magnitude and direction of the velocity, and then they're saying neglect air drag and aerodynamic lift, right? So what they say there tells you because the rocket maintains horizontal orientation, say through the gyroscopes, that's the technology used, the X and Y components are acceleration independent of each other. Obviously, we're familiar with that. We've already stated this. Okay, so let's first find the velocity in the Y direction. So normally, what we're going to do, we have obviously our equations of motion for the X and the Y, but we are looking for this guy. We're looking for Vy, right? So what do you think we can use here, right, for Vy? So they want the velocity in the Y direction, not Voy, Vy. What can we use? How do we find the velocity in the Y direction? What options do we have? Anyone? Okay, I guess I should warm up. Bonani, is it you right now? That's early on. Okay. So we find the velocity of the rocket, and obviously we know that we always take this as a reference, so we know that it's 0, right? And what we essentially looking at here is Vy, and that equals Voy squared minus 2g delta y, right? And what we need is to find Vy. At our Voy is going to be 0 because there is no velocity, initial velocity in the rocket was dropped. Okay, so what we have to then do, we're looking for Vy. We know that this is going to be 0. We know that is 2. We know this is 9,81. Sorry, this is also squared here, squared over here. And for 9,80, forgive me, bad habits. And we times it by that distance over the -1 times 00 times 10 to the power 2. Right, so that's where we're going to find the velocity. So again, this is just only for the Y direction. So can we get Vy? Okay, so I'm just going to put that for you up. Guys, it's important to practice, right? I can only do so much. So you have to make sure you put in the work. So that's, I believe that's 100. All right, guys. So can you get me Vy? So that's the velocity in the Y direction. Okay. Waiting on you guys now. Are you still there? Are you following? Licho Nolo? Kia ora.
So I got 140.
140, right? Is that correct? C. I keep on using 9,81, eh? It's gonna kill me somewhere, but still. How much do you get? So that's 1,000, eh? Not a. It's 140 years. 140 meters per second. Do you all get this? (140 meters per second). Are you all happy with this? Cool. No, Afrika, what is the problem? What are you missing? Yes, okay. But what's missing with that 140 meters per second? I got on 42. It's close enough. I mean, I'll accept that. Yeah. So what's missing with this 140 meters per second? What do you think is missing? Perfect. Yes, Afrika? Afrika, we are waiting on you.
Sir.
Yes, go for it. Yeah.
Sir, are you sure is it fine not being this accurate, sir?
Yeah, I'm okay with it. I mean, what do you miss? I mean,
because I'm not sure if my calculations are correct because I did the exact same thing, same numbers, but I'm not getting the same answer. I'm not sure if it's my calculator or
it could be. Yeah. Just check. Just check if your mode is in degrees or radians and the other one is different modes, but I don't think it should be a problem. You have to reset your calculator and redo the calculation. Yeah.
And
need
so
the direction, right?
how do we approach
Sorry?
questions where we are told that an object has been dropped or has been projected at a certain angle?
Yes, that's
Question
why
like
I'm
that.
asking. Yeah, that's you could have done that one. That's example 3.5.
Oh,
It's a very good. Yeah, we can do that. Yeah. I'm
thanks.
just checking what I want you guys to come to me, but people are not actually coming to me, so that's the problem. Direction west as Africa, raise
So
your
you'll
hand
be
again.
there. So be at campus on Thursday, sir.
That's the plan, yes.
Okay, no problem.
Yeah. Okay. That's the plan. At least I want to see you once. That's correct. And Likonolo is bringing something interesting. So what is the direction? Direction west is negative. How is the rocket traveling? Very good question. But isn't west? Yeah, west is negative. But why is it traveling west? How do you know which what tells is traveling west? I like that. Yes, I like that. In the y direction, it's going downwards. That's correct. That's what I'm looking for. Exactly. So it's negative. So it's negative of 30 because it's below this part over here. If it was on top over here, it was projected upwards, then you would deem it positive. And that's why if you did the other examples, you would have seen these things. This is what I'm checking for. Can you please zoom in a little? No problems. I'll zoom in for you. Okay, so I want us to do the next one. So I'll give you guys 2 minutes to absorb, and then what is this? The other one, so I'll try to do B, right? So B is the velocity in the x direction. So Vx, not Vox. Give it a go. So you want to find the velocity of the rocket at that particular instant. And there's a way to do that, obviously. There's 2 ways to actually do that. So try B. Try B. I think I should give you 5 minutes, and I'll try to show you B with 2 ways. Yeah. is that for, I'm gonna just check the book quickly. Let me just page there. What is it answer there? It should be 386. It should be quite fast. There's two ways of doing this. Remember your formulas for your max. Oh, that's for the projection. Remember those nice formulas you can actually use. I wonder if we can use those. Let me quickly see. I think my mistake is at times 9,8 times let me just see here. What's the problem? Trying to figure out something. Oh, I see my negative. Sorry, negative. Oh, I see what you mean. Sorry. It should be 2 times 9,8 times. I see the mistake. Sorry, I see the mistake, guys. I see the mistake. It's in the textbook. They made a mistake. Yeah. It's on the sketch. That should be times 10 to the power 3 over here. That should be times 10 to the power 3. Where is my pen? This is 3, sorry. This is not 2. It's 1 kilometer, sorry. This is 1 kilometer. I confused the two. There we go. I see it over here. Which is 1,000 essentially. I was busy solving the other problem now. Okay. Yeah, it's dropped 1 kilometer, guys. That's the I used that on mistake there. Sorry about that. That is my mistake. So you guys get the next answer? Why is this not the same? Okay. You guys get the next answer? That's fantastic. Mr. Bochos doing the things here. Did everyone get that answer? I'm just going to show you the two ways to get it quickly. For some reason, I'm not getting these answers here. Okay. I think I'm sorted now. Still not sorted. Anyone else get the answer? Okay, so I'm moving along, right? Hope you guys got. So I'm going to show you the two ways to do it. Let's quickly do that. So we need to find the velocity in the x direction, so that is vx, right? Okay. So there are two ways to do this. We have to find it. So if you remember our formulas, we know that vx is equal to vox plus ax times t. So normally ax was 0, but in this case ax is 20 meters per second squared, right? We have vox. That's obviously projected at an angle of 0, and it's over there. The only thing we need is the time. So for us to find the velocity for the x direction, we need to find the time where this actually happened. So this over here corresponds with a particular time. So we need to just kind of work backwards first, okay? So I'm going to do it on the side. We know that Vy equals Voy, right, plus At, or negative if you want, depends on look at it. We know that's 140. We know that is 0. We know this is minus 9,8, I believe. And then obviously we're left with t over here, right? And what we need to do now is solve for t. So that's why it's important that this sign is negative, so that can become negative. Or you can just keep it positive. You guys have your own particular way of doing it. So you're saying 140 divided by 9,8 and dividing that by t. Okay, so saying 140 divided by 9,8, and then should get an answer of t should be 14.285, or we can call it 14.3 seconds, right? It's one decimal over there in terms of significant figures. Okay, so once you have the time, all we can do is take this value and throw it back into this equation. So we know Vx is equal to the velocity, that is 1, so 100, the 1.00 times 10 to the power 2 times cos of 0, because it's at 0 degrees, plus 20 times the 14.3. Okay, so we can get that. 100 times cos 0 times 20, plus 20 times 14.3. We should get 386 meters per second. And if you think about it, it travels faster than the speed of sound, which is around 300 odd meters per second. Not sure if you're familiar with that. The alternative way of getting this is to find how far it actually traveled in the x direction, right? That's the alternative way. So what we need to do now is the alternative way is just finding delta x maybe. And we have Vox t plus half at squared, or that's obviously x. We still have to find the time at a particular instant. So we know that this is going to be 100 cos of 0 again. We times that by 14.3. We plus a half. And our acceleration is 20. And we know it's 14.3. And this equation will tell us, as it's, even though it's at this particular instant, obviously it's dropped, you know, 1,000 going down, a kilometer, 1,000 meters. It's also obviously moved a particular amount. Can someone get me this delta x, please? I'm just showing the alternative way of doing this. What's delta x? So if I had to ask you for the range or the distance traveled of the rocket, this would have been the answer. But the both answers definitely right. Can I just get the delta x, please? That's correct. I think the ball is the only one who's pushing here, 3474.9 meters. 3474.9 meters. And we can obviously use this equation, the Vox squared plus 2ax delta x. And I'm just going to root it. We know this is 100 squared, because 100 times cos 0 is 1, plus that by 2, times that by 20, times that by 3474.9. And obviously, you should get exactly the same answer, I believe. Can you please just corroborate that answer? But that's important to note, because then you know how far it's traveled in the x direction anyway. So you can just let me know if you got that. Okay. Perfect. Thank you, Wendy. So I hope you guys get this right, and I'll be practicing these things. Okay, then the last part I want you guys to quickly do is essentially find the resultant part, and it says calculate the magnitude and direction of its velocity, right? So we're expecting an angle, and we're expecting, obviously, so that is the total velocity of the rocket. So we know that, let me just throw my rocket. We actually find the rocket's actual velocity and which direction relative to the x-axis, in terms of what it's traveling. So can you guys quickly do that? Easy part. You've done this before. Sorry about that. This isn't a textbook, man. So I thought you guys were checking the textbook. Okay. There you go. So at 3 o'clock, I will I'll solve the problem. I think that's correct. I'm not sure. Should get 411. Yeah, that's close. That's perfect. Yeah, okay. That's nice. Okay, so I got some answers. I can quickly step in and do this. So obviously to find the actual velocity, V, quite proud of you guys, that's good. There's Vx plus Vy. Obviously both square them. And you should take 386 squared plus Vy. Vy was 140 or negative 140 squared. Let me quickly find that for you. Or you've done it already. You should get 410.60 meters per second. And then to find the angle, you're simply going to have to say tan that, and that's going to be negative 140 divided by 386. It's important to keep the sign because it'll tell us exactly where it is. And if we do that, you get an angle of negative 19.94 degrees. And that makes sense. And if you look at the value, it's in this quadrant over here, you know, there. That's why it all makes sense. Velocity y will be there. Velocity x is over there, and obviously it's that angle is over here. So arguably over there, approximately 19.935 degrees. It cannot be a positive angle. Is it clear to everyone? Everyone get that? I'm just looking for something quickly. Everyone get that? Let's see. Thank you, Double. Fantastic. Okay. Now I just want to see something. So I'm going to start in the new section. So maybe on Thursday, Afika, please send me an email and regarding the question. But if you are working with a projectile at an angle, now that we're talking about it, I'll just quickly mention it to you. It's quite simple. So if you look at your equation, V, maybe your Vx equals Vox plus AT. Well, obviously this doesn't count, typically you don't have this. All we have to do is basically say Vox is equal to cos of, that's V initial times the cos or sine of that particular angle. So all you have to do is input that particular angle over there. I hope that's clear, Afika. So if they're saying the projectile is fired at 45 degrees, you'd input here 45. If it's input at 60 degrees, you'd input at 60. Yeah, that's basically all. And if you do example 3.5, you can actually see that quite nicely. That's a nice example. I mean, I can literally just put in a 40 degrees and the whole thing can actually change over there. Yeah, so that's definitely one. And I think I'm still waiting for that extra physics questions. We're still waiting. Okay. Yeah, so let's quickly move on to the next part, which is a little velocity. And then, yeah, we continue with that. So I've lectured this particular section in the diploma. And yes, so I'm hoping that it's gonna work out. I'm gonna use that slide at some point. And I think let me use that slide rather first to talk about it. Then kind of related to what's happening over here. So I think that slide is way better prepared in this. Tafika, remind me to post these slides as well. I use this for the diploma, but there's a whole section on relative velocity in the diploma. Okay. So I'll try to quickly articulate it well. I didn't solve the problems in the textbook. It's still the same though. Okay. Cool. Let's give it a second. Should appear. All right. Okay. So relative velocity. Thursday you'll get the question. Yeah, send it to me before. Please, so I can have a look at it. Maybe I can find some nice stuff there. And someone has asked Bonani, who asked the question? Bonani. Whoever asking the question, just please. Yeah, Bonani. Yeah. Okay, so this is part of topic 3, guys. Not a topic on its own. But I just prepared the slides last year, which is a bit arguably a bit better than what I have here. Okay. So I just want to see something. And then we can quickly continue with the relative velocity. And there's some nice problems also in the textbook under, you know, these additional problems. I'd urge you to look at that as well. Okay. So relative velocity, right? So looking at these figures, right? I'm to ask you, let's start with the plane, for instance. What do you think is happening with the plane? Right? Look at the plane. There's 3 particular ones. So the image on the left, you guys can see. What do you think is happening? Talking about relative velocity, right? Anyone has any idea? Can you guys see it? And the second picture, look at that. Look at the velocity of the rain. What do you think is happening? Who can gauge? Anyone? Fika? Are you always keen?
I'm not sure, sir, if I'm correct, but for the aeroplane, sir, from the left to the right, the aeroplane is decreasing in velocity going down, and on
Nice.
the bigger picture, it seems like it's falling from a point at an angle, going down
Nice.
at an angle, and then
Yeah.
for the rain person, he's running toward away from the rain or towards the rain, which is affecting how the rain hits him. I'm not sure if I'm correct.
No, that's the exact observations what I want to look at. So the title here of today is called relative velocity, right? So it means one velocity relative to another. What we're essentially looking at here, and obviously I'll articulate to explain it, is that in the first, on the left-hand side, the far left, that plane over there. So what we have there is a plane with a wind at the tail, right? And what's it actually doing? It's how when we find the total velocity of the particular plane, we have to now include the wind velocity plus the plane velocity. If we look at the middle one, there's a headwind. So there's a headwind approaching the plane. And in this case, we don't only, to define the velocity, we have to take the velocity of the plane, subtract the velocity of the wind. And what's interesting on the last one is that the wind is traveling at an angle, resulting in the plane to be shifted away from that middle section. So it's just an indication of here we have the velocity of the plane and we have the velocity of the wind, and we have to include that to find the total velocity of which the plane is essentially traveling. Likewise with the rain over there, the rain is traveling at a certain speed going down, but as soon as it runs, there is two velocities: the velocities of the person and the velocity of the rain. And then obviously it looks like it's falling at an angle, but what that is essentially adding the velocity of the person and adding the velocity of the rain. Okay, that's just basic, but I'll try to articulate better. It's going to come out in the slides. So what is a relative velocity, right? So they say this is the apparent velocity from which one object has as seen from another. So that's very important, guys. So when we talk about the relative velocity, we're assuming we're looking at the velocity of one body to another, right? So for instance, when you're traveling in a car doing 60 kilometers, right? That's car A there. And another car is traveling at 80, at 80 kilometers. The two vehicles are approaching each other at 140. Do you guys get that? Does it make sense to you? Who does this make sense to? So that's relative. So relative to car A, we're actually seeing it at approaching at 140, relative to car A. Do we get that? Anyone? This is what you're trying to check. Okay. So what's interesting here, it says neither car is moving with a speed of 140 kilometers per hour relative to the road. Obviously, sorry, I should have mentioned that. However, the occupants of both cars, they're looking at each other, they appear to be traveling at 140. And then we basically, the car's relative velocity, or the relative speed to the other car is 140. And I think I should have been more correct here. The resultant velocity, when I'm talking about that, is actually in relation to the Earth. So the plane's velocity plus the air or the wind will be relative to the Earth. So it'll be the actual velocity. And then likewise with the rain. So the man plus the rain, that's all relative to the Earth. That should have also been mentioned. And relative velocity is a very important topic in mechanical engineering. I'm not going to go into this, but it really occurs. It's a very important principle. We look at machine parts and even our fluid moves. This is what we essentially come into, is the examples like that. So, but obviously, before we determine the relative velocity, we need to understand what the resultant velocity. So what I'm going to just basically demonstrate to you, just basically a small example of what we need to do. Okay, so saying if an object is moving in a medium, which is also relative to the Earth, the object's velocity relative to the Earth is the resultant of the two velocities. So that's what I'm essentially talking about. So typically, the mediums that we are referring to is the air and the water, and obviously when we add up the velocity of let's say a boat to the river, we add it up and it's all relative to the Earth. Okay, so what's an example of resultant velocity? Obviously, you guys are aware. So you can imagine, look at the image on the right there, before we look at the image on the left. For example, you're rowing a boat, you're on a ship or a yacht, and you've turned across a river, or maybe the sea, but obviously maybe moving from one point to another. And you're moving from A to B, but then you are rowing at 3 kilometers per hour, or 3 meters per second rather, as per sketch. But basically the river itself has its own velocity, which is going at 5 meters per second to the right. So what's going to happen is that you won't land at point B, because what's going to happen is that the tide is going to push you away, and then you land up at C, right? But if you want to know exactly the speed which you'll land and where you'll land, you basically going to have to take the vector sum of the two. So they're saying there, if you take the vector sum of the boat, of you rowing the boat, plus the river, you end up with the resultant velocity. And obviously that will give you a nice angle, and that angle will also tell you how far you actually moved away from the thing. then if you look at the image on the left, that basically articulates the same thing, right? So there's a motion of the boat with current on top and shows how it pushes the way. And that's the vector sum of the two velocities. And then the one without current, you just kind of go straight across, you move from A to B. Is it clear to everyone what the concept of relative velocity is? Like, well, the resultant part of the relative velocity. Do we get that? What the resultant velocity is? Please tell me if it's not clear. Do we all get that? Umfundo, Africa, Tebogo, Luganda, Lefonolo, Miss Anthony, Precious. That's a Y. Okay. Tabo. So that's the concept of resultant velocity. We're going to need it for relative velocity. Okay. So in keeping on the previous sketches, when we're looking at because we need to find the resultant velocity for the relative velocity, and you understand that shortly. So for instance, when you're looking at those two cases, we have the plane and the wind, and I'm going to ask you a quick question. So they say a tailwind is merely a wind that approaches the plane from behind, thus increasing its velocity, obviously. So if the plane is traveling at 100 kilometers per hour with respect to the air, and the wind is traveling at 25 kilometers, also obviously, right? Then what is the velocity of the plane relative to the observer on the ground? So when we're looking on the ground going up, what velocity do we actually see? Who can tell me based on that two figures? Quick. What velocity do we get? Remember that first illustration which I mentioned? I'll give you guys a minute to think about that. Correct. So what we do in that case, we add the velocities. And the reason why is going in the same direction. So we're having the 100 plus the 25, and then from what when we look up, we see a total of 125 kilometers per hour, right? Relative to the ground. Very important. Let's look at the next. Oh, okay, that's basically illustrating what it is there. So saying there that the resultant velocity of the plane is the result of the wind velocity and the plane's motor, obviously the velocity of the plane, and that's the vector sum of the two. So the reason why it's easy to add is in the same direction, so therefore we can just simply add them. So the resultant velocity is 125, but what we say, right? They're saying the plane travels with a velocity relative to the ground, which is the vector sum of the plane's velocity relative to the air plus the wind velocity. So that's very important, where it's all being relative to. Okay, so this one, quite easy. Looking at that over there, if we had now a headwind, right? So the wind approaching the front of the plane. What do you think? Well, obviously the velocity will decrease in this case. So if you have a headwind, the plane won't travel as fast. I'm sure you've all experienced this when you walk and you walk against the like the wind, and you can feel you're going a bit slower. In this case, we take the 100 minus the 25, and we get 75 kilometers per hour. So again, from the observer from the ground, we will see 75 kilometers per hour. Is it clear to everyone in terms of the resultant and the relative? Is it all clear? I hope it's clear to everyone. Yeah. because we'll be doing things like this basically. And the last one, which is the more interesting one, so if we had a velocity, maybe a side wind, maybe, right, and it's going 25 kilometers to the west. In this case, the plane will travel or at a particular angle, and will be obviously the velocity will increase. So still take the vector sum, but now in this case we say 100 squared plus 25 squared, and we root it, and we should get 103. And then obviously, and we can find the angle using Pythagoras. We should get 114 degrees. And what it means, if the plane travels straight and there's a velocity going 25 kilometers west, we will be pushed to the, what is this, to the left there, and we will move approximately at an angle of 14 degrees. And once again, when you look at the bottom to the top from as an observer, you see the plane moving. It'll be shifting at 14 degrees away from where it's supposed to be at a speed of 103 kilometers per hour. Right, is that clear? So the resultant velocity is 103, and obviously relative to the ground, that's 103. Are we all happy with that? Can you see that? That's basically most of the stuff you'll be doing. I'll do some nice problems with that. Is it all clear to everyone what's happening here? So it's just basically like resultants of velocities. Yeah. Any questions, guys, before we move on? Let's go. Yeah, there we go. Okay, cool. What's next? So that's just relative velocity, and then let's see what's next. And yeah, it's just again the illustrations of what's happening here. So I'll post this slide. So it's basically the same thing again, and then obviously, yeah, just articulating what's happening with the crosswind, the headwind, and the tailwind. It's important. And then obviously, in this case, we're really familiar with this, but just specifying velocity vectors, where we have our notation. We've discussed this initially in one of the first lectures where we looked at east and north and west, and how we measure something. So if we say, for instance, I'll just recap again because it does come up here. When it's saying, let's say, for example, you are in the first illustration, you are starting east and you rotate 32 degrees towards north. Let's say you're moving in that direction, what you can say is that the direction is carried as east 32 degrees over north, right? So it's obviously relative to north. However, you can also say the same direction, looking from the north, you can say it's north 58 degrees to east, right? And obviously that's going to be the 90 minus 32, which will give you 58. And you can do exactly the same in the second illustration there, where we have west north, where you can say it's west of 75 degrees north, and if you're referring to the south side, you can say south 15 degrees towards west. I hope that's clear to everyone. Yeah, we did talk about it last time. Okay, this is a ship bearing. We've talked about that, and this is a relative bearing, which is not important. So relative bearing is just that we treat the compass as a full 360 degrees around there. So, but obviously this is more important than that. This might happen, but I doubt it. But you might get, maybe in the tutorials, maybe I might give you things in this particular units. Highly doubt it, but I think it is important as marine engineers to know this. When we talk about a ship moving or boat, we don't talk about meters per second or kilometers per hour. They typically use knots. So I'm just making aware. In the marine sector, when we talk about a ship moving, you typically are knots, and the navigators will talk about it. But what a knot essentially is, it's 1.582 kilometers per hour, and it's based on the dimension that is called a convenient fraction of the Earth's circumference. That's what it essentially is, right? What we know also is something called a nautical mile, but that's where the nautical sciences probably come from. We know that 1 knot is 1 nautical mile per hour, and what they say there, 1 nautical mile is the length of an arc, right? So that arc is that red part there. at the Earth's surface subtended by the angle of 1 minute. It's not really important to remember, but just important to note that 1 knot is equal to 1.852 kilometers per hour, and 1 nautical mile is essentially equal to 1,852 meters. So maybe if you get a question, you can obviously just play around with those things. Okay, so in talking about the velocities again, I think what's just important to note is that when we're talking about relative velocity, we always referring to a particular point, and this is what it's about here. So the same velocities relative to the Earth are referred to the absolute velocity, and the term relative applies to a motion of one point relative to another. So what we typically do, we everything to the Earth is what we see say is the absolute velocity. So when we add velocities, we always say relative to the Earth, and that's what we call absolute. That's what we call. Obviously, the sun is moving with respect to the Earth. A lot of things, satellites are moving with respect to something else, but for us, it's the Earth. Okay, so that's some illustrations of. I don't know what's the point of this. Things moving at different. Okay, so that's just in conclusion. The resultant velocity is a vectorial sum of the velocities. Number two, the relative velocity is a vectorial difference of velocities, and we'll talk about that. And number three, the absolute velocity is the velocity of the body relative to some fixed datum, and that's usually the Earth. Very important that I expect you to remember this. And yeah, that's the resultant is a vectorial sum, where the relative velocity is a vectorial difference. And you'll see that in your book, that when they talk about the difference in velocities, they talk about the difference in terms of the two. Okay, so let me just quickly look at something, and then yeah, I wonder if I can maybe I can just do an example quickly. Yeah, so I'm going to do one example explaining, and then we'll continue on Thursday with this. Okay, let me just leave this. So your book kind of talks exactly the same thing, but this is how it generally approaches problems anyway. So move this. Okay. I typically have one body moving, it seems, not two. Yeah. Okay. So I'm gonna give this one and give this one for homework. Okay, fine. And then we're done for the day. So we're doing example 3.8, which is the most important one. Wow, there might be two, which is important, but I'll see. Okay. Let me quickly just lock this. Yeah. So we're gonna do this one, and then we are going to give you the one homework, and then we're basically done. So this is relative velocity, right? So in this question, again, it's two dimensions, meaning obviously this motion is happening in two directions, right? So in this case, what we have, the boat, talked about this boat before, it's heading north, right? As it crosses a wider river with a velocity of 10 kilometers relative to the water, right? So we know it's moving at 10. The river itself has a velocity of 5 kilometers due east. So what they're representing is the boat's going straight, and the river is pushing that way. So what they're asking there is determine the magnitude and the direction of the boat's velocity with respect to the observer on the river bank. So we are standing over here, and what we're going to be seeing is how this boat is actually moving in whatever direction. So what I'm saying, the boat is trying to go from south to north, but the river is pushing east. So obviously we're going to see the boat moving at a particular angle. So we can't see the content. I'm sure everyone else can see it. Can you guys see it? Just refresh. Yes, when you can see it. Just refresh Lego Nolo. And so now we need to find the relative or resultant velocity. Okay. Can you guys see it? What is Konolo? Can you see it before we move on? Who else cannot see it? Just refresh your thing and then get back in. All right. Okay, so quite simple. All we have to do is just remember that the relative velocity in this case, I'm going to call it, I mean, they call it a few things here, but I mean, we want VBE, which is essentially the sum of the, I'm just going to call it, let me see what I should call it here. I'm going to call it VO, which is observer, or they call it VBE, is equal to the boat's velocity plus the velocity of the river, right? So for the book, this is called BE, the boat is called BR, and this is called RE. Right? So I'm just calling it the boat BR, and they want to know VO, basically. So what we all have to do now to find the resultant is imagine it's on a Cartesian plane. Book makes it look a lot difficult than what it actually is. And we're going to put the velocities here. So we know that this is VR over here, and that's at a speed of 5, I believe, 5 kilometers per hour. And we know that the other one is basically like this, and that's going at 10 kilometers per hour. Okay. So this is quite easy if you can actually see what to do. This is a simple Pythagoras, but what you want to do is have your components. So your Vx, I'm just going to say V, this is V, so I should put V boat. This is the boat. This is the river. I'm just going to have it like this. So we have Vx, Vy. So it's the same components as the forces. So I'll ask you, just make the line shorter. For the boat, do we have an x component for the boat? Yes or no? Do we have an x component for the boat? No, exactly. So then we put 0. Do you have a y component, and you make sure that it's plus 10, right? Do you have an x component for the river? Is it positive or negative? Is there a positive component? Is there x component, sorry, positive component? Plus 5 exactly. Is there a y component? There isn't, right? So all we have to do is take, right, the velocities over there, vx squared plus vy squared, the sum of them, just like we found in the forces. So obviously the sum in this case will be just a 5, and the sum over here will be 10. It's important to keep the signs. and then you're going to say 5 squared plus 10 squared. When can I get that answer? You should get 11.18. Did all you guys get that? Are we all happy with this? Right, so we're saying the velocity with respect to the observer there, the boat is moving at 11.18. Obviously, we just need to find an angle. Straightforward. The section is not difficult, guys. Promise you. Straightforward. What is that now? It's 10 over 5, right? 5 over 10, sorry. It's y. What's it? Should be y over x. Right? 5 over 10. What's no. Y is 10. 10 over 2. 10 over 5. Sorry. What is my angle? Yeah, so it's quite simple. If you start doing these problems, I need to give you a few of these problems as well. You should get 63.43 degrees, right? But that's relative. I'll show you now. 63.43 degrees. So the book has 26.6, but that's depending on how you want to look at. So the angle we got was this angle over here, right? It's positive. It's this angle over here. I'll show you now. This is the relative to east. Remember, it's always relative to the east. So we got 63 point. What's it again? 63.43 degrees, and obviously you say 90 minus an angle, you should get the exact answer there. You should get the 26.57. So relative to north, it's 26 or 26.6 east of north, depending the way you want to look at it. So both those angles are correct. All right, so that's the one part of relative velocity. And we'll touch on a few more on Thursday. But what I want you guys to do is two things, right? Make sure you complete the exercise 3.8. That's the question after that. Or you use inverse. Exactly. Okay, yeah, well, that you did use inverse. Okay, I don't know what you mean, but do exercise 3.8. And then also,
So,
yes, go for it.
oh, so I was saying use inverse by saying instead of saying second function of tan 10 over 5, you could use 5 over 10. Then we get that 26,56.
Oh, yeah, I know we can do that as well, yeah. But I mean, I just always keep it y over x. Same. Then I think what I'll do is yeah, do that question next. Then I might post a tutorial yeah, so a tutorial type question as well tomorrow on like a boat movie. And then what I would appreciate, guys, you can send me an email for anything extra I must cover for the other stuff you didn't get. But I can see some people are practicing, some people are not, right? So please send me an email, because next week, surely we are starting with forces, which is nice. Not difficult, but make sure you're able to do that. You're looking at friction, kinetic friction, normal forces, that kind of thing. Stuff you're familiar with, basically. Tension forces, yeah. It's the last chapter before you're gonna write. then we should be able to solve them. But yeah, anyway, I'll see you on campus on Thursday. That's the plan. But in test 1, which test 1? It'll be topic 1 through topic 4. The test on the 30th of May, I believe. Yeah, it'll be 4 topics for the first semester. And the next semester, I'm hoping to complete. There'll be definitely more, at least, I don't know how many topics I'll actually cover. Maybe 1, 2, 3, 4, maybe around 6 topics. Yeah, maybe 6 topics in the next semester. But it depends on how the topics go, man, and how good you guys are. Okay, so yeah, guys, so do exercise 3.8. Then I'll see you on Thursday. We will continue with more relative velocity, and I'd like you guys to send me at least 1 or 2 questions, but ideally 1, so I can just kind of go over the 2-dimensional thing. And guys, please, please practice. I'm not going to say it again. Go over the lectures, do all the examples, do the exercises, and then go to the examples. I mean, go do the examples, do the exercises after the example, then do the exercise at the back of the book. The test will all form part of the tutorials and all the stuff you do. Essentially will be nothing new. But guys, please, 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 please practice and also attend the tutorial sessions. That will obviously help. All right, guys, thank you for attending today. And I'll see you on Thursday again. Bye.